So, assalamu alaikum everyone. So, in the previous sessions, we have seen the basics of linear algebra. If you see them, so we have seen what a vector means, then we have seen what Cartesian planes are, then we went into different concepts of the algebra. So, having their basics, now we can delve into the mathematical details of algebra. So, from this session onwards, what we'll do is we'll go into the mathematical details and how to compute these things. For example, you learnt about bases, you learnt about linear combinations, you learnt about inverses and stuff like that. Now we want to see how to compute these things. So you have the intuition, you have the geometric intuition, and you know what's happening in the space in 2D and 3D. Now we want to do it mathematically, and we want to obtain the answers to the equation. So I said that the fundamental problem of algebra is solving linear equations. Solving linear equations. This is what we call as fundamental problem that algebra basically solves. Fundamental problem of algebra. Okay, so now we have to solve these linear equations, if you ask me. So there are a lot of methods. So maybe I'll just move this camera a bit so that this screen is perfectly visible. Okay, nice. So this is what we'll delve into the details of now. So how to solve these equations? Let's consider a simple case. Let's suppose we have an equation x plus 2y is equal to 3. So this is our first equation. Let's suppose our second equation is 4x plus 5y is equal to 6. This is our second equation. Let's call this equation 1 and equation 2. If you remember what we used to do in our class 8 9, so what we did is we used to do what is called as elimination and back substitution. What we did is elimination and back substitution. Now you know that these equations, they sort of define a plane. So these planes do intersect, and we have seen those two pictures, row picture and a column picture. So what was the original way that we used to do it? So if this is equation 2 and this is equation 1, so what we'll do is we'll subtract, let's suppose, 4 times this equation. Like we'll multiply this equation with 4 because we want to eliminate one of the variables. So to eliminate, will multiply this first equation. Let's multiply first equation by 4, and then maybe subtract this equation from equation second. This is what we'll do. So this means multiply equation 1 by 4 and subtract it from equation 2. So what will happen to the equation 1 is equation 1 will now become 4x plus 8y is equal to 12. This is what will happen to this equation. And now the second equation is as it is, so we'll write the second equation. The second equation was 4x plus 5y is equal to 6. So we are subtracting this equation. So we are subtracting this first equation. So these signs will change. We are subtracting this equation. So these things will get cancelled out. Okay, so if you see, these things will get cancelled out, and now we are remained with 5 minus 8. This is minus 3y. That's equal to minus 6, and y is equal to 2. So we first eliminated one variable. So we eliminated this x out of the equation, and after that, what we did is we'll substitute this variable y variable into any of this equation. So this will substitute in the first equation. So we have x plus 2 multiplied by 2, because y's value is 2. This is the equation. X plus 2 multiplied by 2 is equal to 3. So now we have x is equal to 3 minus 4, that's equal to 1. That's equal to minus 1. So we have y is equal to 2 and x is equal to minus 1. This is the solution of equation. Now we want to understand what happened in the algebra. So what happened in the linear algebra? So in that, we had an equation. So this is equation of a line. So if you see, let's suppose this was our Cartesian plane. Let's make the Cartesian plane over here. So let's suppose this was one line and this was the other line. So here, this is the point of intersection. So actually this point is this x comma y, the point that we found. So let's suppose this was our equation 1 and this was our equation 2 line. This is what we found. If we talk about that row picture, so this was our row picture, if you still remember that. So we took one row at a time. So we made a line out of this row because this represents a line. So again, then this also represents a line. So we made a line and we saw what's the intersection point of these two, and we found the answers. So what we did is we did the elimination and then back substitution. That was the traditional method that we used to know. And we can use the similar method, and we also can compute these things by using determinants. We can also use determinants. I won't tell you the exact process, but I'll just show you things, how these things are being done in determinants. So y will be computed, because if you see these numbers, the numbers are 1, 2, and we have 3, 4, 5, and 6. So how to compute these numbers? So y will basically be equal to determinant of 1, 3, 4, 6 divided by determinant of 1, 2, 4, 5. So if you compute the determinant, that is 6 minus 12 divided by 5 minus 10, that's equal to minus 6 divided by minus 3, that's equal to 2. This is the value of y by using determinants. So I brought something like I brought some numbers in the determinant which I took from the equations, and how this is computed, and how do we got these two determinants. We'll get to the details of those things, but know that we can also compute this by using the determinant, and we can similarly use for the computation of x, we have this determinants 2, 3, 3, 2, 6, 5, and then we have 1, 2, 4, 5. So if you now compute determinant, that is 3 multiplied by 5 minus 2 multiplied by 6 divided by 1 multiplied by 5 minus 2 multiplied by 4. That's equal to 3 divided by minus 3, that's equal to minus 1. Okay, so this is how we use determinants, but you don't know the actual process where we got to this determinant from. We'll learn that when we'll go in the deeper details of how to compute the determinants, stuff like that. The thing that I want you to at least have an understanding of here is that this is the equation of linear equation, which there are two equations and there are two unknowns. The equation it has variables x and y. So how to basically now show this equation? If you want to show this equation, so the equation basically was 1x plus 2y is equal to 3. This is the first equation, and 4x plus 5y is equal to 6 was the second equation. Now algebraically, how will we show it? So we'll sort of take these coefficients, and these coefficients we'll club them together. We'll make 1, 4, 2, 5. This is called as coefficient matrix. Coefficient matrix, because these were the coefficients of these unknowns, and then we'll put x and y over here. Okay, and we'll put equality 3 comma 6. Now you know that how this matrix multiplications work. Now you can work it reverse way, and you can see that if we multiply 1, 2, and you will get these two equations back. This is the equivalent representation of these equations in our linear algebra form. Now we will see how the elimination will work in algebra. So in the initial step, what we do, we multiplied something. So as we have this written in now notation form, so this is called as unknown matrix or unknowns. Okay, these are the values that we want to achieve. Okay, so these are the three things. So we have this equation. Let's suppose we have some other equation, 5x plus 3y plus 2z, 1x plus 3y minus z, 2x plus 4y minus 12z. Let's suppose this was equal to 1, 4, and 3. So again, if I want to rewrite it in the algebra form and the matrix form, so what I'll do is I'll collect these coefficients in one matrix. Okay, so this will be like this: 5, 1, 2, 3, 3, 4, 2, minus 1, and minus 12. So this will be the coefficient matrix, and then I'll put the unknowns, the variables, basically x, y, and z. Then I'll put the values 1, 4, and 3. Okay, this is how I'll write these equations from now on. So I need not to write the equations in this format. Okay, so this equation, this is sometimes written as A. This matrix, coefficient matrix, is written as A, and this unknowns are written as x, and these are written as v. So in a succinct way, I can write ax is equal to v. Is this clear? Is it clear?
Yes, sir.
Nice. So this is the succinct representation. Now we saw how elimination was being used when we were sort of in our younger age. Now we want to see how does this elimination work. So again, I'll just reiterate those two pictures that we had. We had the column picture, and the row picture, and then we had row picture. Okay, have these things in mind. So in the column picture, what we did is we just wrote the equations. If we had that line, so we sort of constructed that line. Line 1 was like this, and then we had other line, and we sort of found this point. So in the row picture, we actually represented everything by using the vectors. So we used, let's suppose we had a vector like this, and then we had other vector like this, and we wanted to reach this vector by using these two vectors. Okay, so we use linear combination of this and this vector to reach this vector. That was our row picture. Now we'll solve this by what is called as Gaussian elimination. Okay, Gaussian elimination. Gauss was the first one who discovered this method, and it was so natural, and it could have occurred to anyone, like how to solve these equations. Let's take an example and see how the Gaussian elimination is being done. Okay, let me take an example. Okay, I think I have written example somewhere. So let's suppose we have an equation like this. 2u plus v plus w is equal to 5. That's one equation. And then we have 4u plus minus 6v and 0w is equal to minus 2. Then we have minus 2u plus 7v plus 2w, that's equal to 9. So these are three equations. So now in order to do the Gaussian method, in order to do collect that, we'll collect all of these coefficients, all of the coefficients that we have. We'll compute the coefficient, but we'll represent this as ax is equal to v. So what will be the value of a? So the value of a here will be 2, 4, minus 2, 1, minus 6 and 7. And then we'll have 1, 0 and 2. This will be u, v and w, and this will be equal to 5, minus 2 and 9. So how the Gaussian elimination works is, so the first thing is we want to create what is called as upper triangular matrix. Upper triangular matrix. So what is the meaning of upper triangular matrix? Upper triangular matrix basically means if there is a diagonal, the diagonal is like this, all the entries above this diagonal, they are non-zero, they are non-zero, and every entry below this diagonal is 0. This is called as diagonal. Okay, so let's take an example of matrix. So here we have 1, 2, 3, and then we'll 0, 4, 1, 0, 0, 2. So this here is an upper triangular matrix. So what Gauss thought is that, as you know that this is corresponding to u, v and w. So what we'll do is we'll make these entries. So let's suppose this is our diagonal. So this is our diagonal, this entry. We'll make this entry, and this entry as 0. Now we have to perform certain moves. And what are the moves possible are that we can multiply a row by a scalar. So I'll just erase this upper triangular thing. So how to do this Gaussian elimination? It's just like the other elimination that we used to do, but it's now in the matrix form. The first thing that is allowed is we can multiply any row by a scalar. But scalar should not be equal to 0. You cannot just multiply with the 0. That's the first thing you can do. These are the allowed things that are there in the Gaussian elimination. Second thing is you can exchange rows. You can exchange rows. Okay, you can for example make this row over here, so you can just swap these rows together. So the other thing that you can do is, the third thing that you can do is you can subtract one row from other, one row from other row. Okay, or you can multiply, and even you can divide. Multiplication basically it implies that you can also divide. Similar thing, you can subtract or you can add. Okay, just keep these things in the row. So these are called as, these things are the possible operations that you can do. If we again go back to the first initial step that we saw, is we basically did the same thing in here. So these were our two equations. We multiplied the first with 4. That is, it was basically multiplication with a scalar onto a row. And then what we did is we subtracted one row from the other. So we subtracted. But the Gauss, what it did, he generalized in the matrix notation. So this was the notation he gave. Now in order to find these u, v and w, so we'll perform these operations so that we get the lower triangular matrix. So what is the benefit of getting lower triangular matrix? Let's suppose we got A, B, C, 0, D, E, 0, 0, F. Okay, so we got this. Now you know that here you have U, V and W. Now you know that this W, value W, it directly corresponds to this F. Okay, now you can back substitute the value of F, a value of W in here. So you know this corresponds to U, V and W. Now you have the value of W over here, and you can easily compute the other by back substitution. So here, after converting a matrix into lower triangular, now you can back substitute the values. It's basically the equivalent method that we used to do but Gauss did it on the matrix form. So here we want to get this matrix into this lower triangular form. That's what we want to do. So how to eliminate that? Okay, let's do that. So you can also write these operations. So the our matrix was 2, 4, then minus 2, and then we had 1, minus 6, and 7. Then we had 1, 0, and 2. This basically was, and then we'll sort of augment this. So this is called augmentation. We'll augment the answer as well. So the answer initially was my 5, minus 2, 9. So whatever will be happening to these rows, and we'll accordingly do the similar thing to these values 5, minus 2, and 9. The first thing that we'll do is we'll multiply we'll multiply this first equation by 2. So we'll multiply this equation by 2. Okay, so we can say, let's call this R1, this is R2, and this is R3. So how do we write this? We can write this like this: R1 goes to 2 times R1. Okay, that's the first move. And then what we can do is we can subtract this 2 times of the first equation from the second. So this is our second row. Okay, we can subtract this and we can write R2 basically is now R2 and subtract minus 2 R1. So this is what we'll be doing, the final move, and we can just erase this one. So here there are 2 steps going on. The first thing is we are multiplying R1 by 2, and then we are subtracting that R1 from R2. That's what we'll do. Why are we doing so? Because we want to get this entry 0. So these entries are called pivots. Okay, so because in the lower triangular matrix, what we have to do is we have to make this entry, and this entry as 0. Okay, the first step here is I want to make this entry as 0. So how to make this entry 0? If I have had 4 on here, so I would have just subtract the equation, but it is 2. So I'll multiply the whole equation with 2. So this will become 4, this will become 2, this will become this. So now what will R1 will remain unchanged. If you see, so R1 here 2, 1, 1, and 5, it will remain unchanged. So this 5 is the answer 5. So I can write it with different color. So maybe I won't change the color again and again, just write it like this. So R1 is unchanged because we did nothing to R1. So the first equation we did nothing to it. But to the second equation, what we did is we subtracted twice of R1. So basically here it will become 0. So the first equation became now, so the R2 minus twice R1 is equal to, R2 is 4, minus 6, 0, and minus 2. So this equation multiplied by 4. So this will become, so let's put commas here. So this will become 4, then comma, not minus 2, 2, comma 2, comma 10. Okay, now we have to subtract this. This will become 0. So the first entry here became 0. That's what we wanted. So this entry became 0. Now this is minus 6. This will become plus basically. So this was R2. This is our R2. If you remember, this is our R2. This, all the entries are negative here now. So minus 4, minus 6, and this will become minus 8. And this will become minus 2. And this will become minus 10. Minus 10, this will become 12. Minus 12. Okay, and third row will remain as it is. So this row, minus 2, 7, and 2. Minus 2, 7, 2, and this is the answer column. Let's separate them like this. This is 9. So that was the first move. The first thing was to get this pivot as 0. This one as 0. That was our first move. Now what's the second thing is I want this entry to be 0 as well. This entry and this entry should be 0. Okay, so what should I do to get this entry as 0? And directly I can just add this thing. I can just add the column 1 to the row 1 to the row 3 to get this. So what will I get if I add this R3 plus R1? So I'll just add them. So what will I get is 2, 1, 1, because first row won't get changed because that is not our goal. Our goal is to get zeros in the pivot positions. So now this is 0. This is minus 8. This is minus 2. Again now this will become 0. 2 minus 2 is 0. Okay. We are just adding them together. 2 minus 2 is 0. 1 plus 7 is 8. This will become 8. And then 2 plus 1 is 3. So this will become 3. So this will become 5 minus 12. And this will be 2. 9 plus 5 is basically 14. Okay, now we got other 0 here. So last step that I want to get is I want to get this 8 also as 0. Okay, I want to make this is again a pivot. I want to make this 0. So how to make this 0? I can just add these two things together. So I can write R2 or R3 is just R3 plus R2. So if I do that, what will happen to the matrix is it will become 2, 1, 1, and 5 will be right there, and then we'll have 0, minus 8, minus 2. Then these things will get 0 plus 0 is basically 0. This will be 0. 8 minus 8 is 0. 2 minus 3 is 1. Okay, and this will become minus 12, and 14 minus 12 is basically 2. So that's what we got. So now this became a upper triangular matrix. We'll call it U. So this became U, an upper triangular matrix, if you see this. Okay, now we know that 2 1 1 0 minus 8 minus 2 0 0 1, if we multiply it by U, V and W that we had originally, it will be equal to 5 minus 12 and 2. Now we can do the back substitution. Directly you can say that this 1 and this W, 1W is equal to, you can directly say that, because if you want to like compute the entry in here, you can just take this row and you know that 1W is equal to, so 1W is equal to, so W is basically equal to 2. Okay, so W here became equal to, now you can use the method of back substitution. So back substitution. So in the back substitution, now you know the value of W. This equation basically represents 0U minus 8V minus 2W is equal to minus 12. Now you know the value of W, so that's 2. So you can put minus 8V minus 2 multiplied by 2 is equal to minus 12. So this will be equal to minus 8V, and then this will become minus 4, and this will become plus 4 onto here. So this will be minus 8. So V basically is equal to 1. And accordingly you can compute the U as well by using the back substitution. Is the Gauss's elimination method clear? Is it clear? How do we
Yes,
use
sir.
this Gaussian elimination method? Was it clear? Nice. This is how we use basically only step here. These are the moves involved. These are the moves allowed. So first, you can multiply any row by any scalar that should not be equal to 0. And again, you can exchange the rows and then you can subtract. And where do we need to exchange these rows? So there can be two cases now. There can be failure cases. So what are the failure cases? Let's suppose we are doing some elimination. So let's suppose this is A, B, C. This is D, E, and F, G, H, I. I'm taking the 3D case. So let's suppose we wanted to make the elements 0. If for example we made this entry 0, and let's suppose this also became 0. Like for example, if we had a failure case and these things became 0, all of the row became 0, let's suppose. Okay, now whole of one variable got eliminated. Okay, so one row became 0. So these can be the failure cases. Either there can be two things now. So there can be either no solution or there can be infinitely many solutions. Infinitely many solutions, and we'll see where will that happen. Where will be the case where there will be no solution, and where will be the case that where there will be infinitely many solution. So if you also remember the picture, so for example here, if the lines were like this, so there will be one solution over here. Okay, so if the lines will be like this, let's suppose we'll make lines like this. If the lines are like this, so there will be no solution. Basically they are parallel lines, they are not meeting anywhere. Let's make them parallel. Okay, these are the parallel lines. If the lines will be like this, so let's suppose lines are like this, one line is this and second line is on top of the line, so there will be infinitely many solutions. These are the three cases basically. So in a good case where they are meeting at only one point, these can be lines, these can be planes, these can be hyperplanes, as you know. So all of these things can be found. So these two are the failure cases where Gaussian method will fail. And sometimes when we do this forward elimination, so you can cure it. And sometimes, for example, if you got a row, if you got some row over 0, like here, if it was A, B, C, D, E, F and G, H, I. So if there was a case, let's suppose you are making this entry 0, and for example this entry also became 0. Okay, and let's suppose, let's make a matrix bigger to explain the concept. Let's say this is W, X, Y, P, Q, R, S. Now you have a lot of pivots, you have these pivots. So let's suppose you made this entry as 0, this D entry you made it as 0, and you also got this Q as 0 now. Okay, you got this Q as 0. So now what you can do is you can either temporarily stop the elimination process and just exchange these rows. Now because you know that we have to make this entry 0, so it is better to exchange this row, because this entry also became 0, this Q, so it's better to exchange the rows. Okay, so where do the elimination stop? So elimination stops if there is a loss of pivot, if we do not have pivot. So there can be two cases. The one case is which can be curable. So in the curable case, we'll just swap the rows. Okay, we'll just exchange these rows. In the next uncurable case, we cannot find any row, and that will basically break down the process of elimination. Let's take the curable case first. Let's suppose we had three equations in which we had u plus v plus w, that is equal to, let's suppose something, and then we had 2u plus 5w, because this is not our concern, so we'll find this, but this is our concern so far. So how can this become curable and incurable? So we have, these are the equations. So if we write this in matrix form, so this will be 1 2 4 1 2 6 1 5 and 8. This is 8. Okay, so now we have to sort of, this is what I call as curable. So here we can exchange the rows. So let's take this first pivot. So we have to make this 0. So what we'll do is we'll multiply whole of this by 2 and then subtract it from the second equation. So R2 basically will be equal to R2 minus twice of R1. Okay, so if you do this, so the first row will remain as it is. Okay, what will happen to second row? 2 minus 2 is 0. Okay, 2 minus 2 is again 0. Then 5 minus 1 basically is 5 minus 2 is 3. So this is what happened to the second row. And in the similar fashion, we wanted to make this entry as 0 because these are our pivots. So what will happen to R3? So we'll write R3 minus 4 times R1. We'll again do the similar thing. So this will become 0. Okay, now we have 6 minus 4, that's 2. And we have 8 minus 4, that's 4. This is what will happen to the equation. Now you know that because the first entry that we had to make 0 was this. Okay, because we have to get a lower triangular matrix. Now there is this case and we had to make the other entry. For example, here this entry was supposed to be 0. Now we have to sort of pause for the elimination. The thing is, we can make it 0 by making an exchange, but we have a 0 already here, so we can make an exchange of the rows. So we can just say exchange R2 with R3. So that will give us 1 and then 0 0 like this, because we are exchanging these two rows. So 1 1 1 will be the first row, that's intact. So 0 2 4 will happen, go here, and 0 0 3 will happen here. Now we have the lower triangular matrix. So you saw this triangle formed here. So this is the curable case. If there is a if 0 happens somewhere, we can make the row exchange. So these are called row exchange. Then there is a case of incurable case where we call these matrices as singular because their determinant is 0. I actually sort of explained this in the previous session as well, what singular means. Let's take that incurable case. Let's suppose I'll directly write the matrix now. Let's suppose I have the matrix 1 1 and 1, 2 2 and 5, and 4 4 and 8. Let's suppose this was our matrix. So if we perform the first, these are called elementary transformations. Whatever I did so far, this row exchange, whatever are the rules I wrote here, these are called elementary transformations. The Gaussian elimination that I wrote, the 3 rules here that I wrote. So these 3 things, we call them as elementary transformations. I'll talk about why they're called the element transformations, but just remember that there are 2 cases. Now Gaussian elimination works, so but in 2 cases it's sort of stuck. In the first case, where one of the pivot becomes 0, we can sort of cure that case by just exchanging the rows. And the second case where this gets sort of incurable is that if, let's suppose, we performed an elementary transformation where we want to get this entry and this entry as 0, we'll do the elementary transformation. R2 will become 2 minus 2 times R1, and R3 will become R3 minus 4 times R1. So what will happen is, what I'll get out of this is 1 1 1 will remain as it is. So first row will remain as it is. Okay, what will happen to the second row? This will become 0. Okay, this will also become 0. 0 0 3. So this will become 3 because 5 minus 2 is 3. So now this will become 0 and this will also become 0. This is 0 0, and now this basically will become as 4. 8 minus 4 is 4. So now you saw that you cannot exchange the rows now. Okay, now basically pivot became 0. So our equation should have been like this: 1 A B C, 0 D E, 0 0 F, something like this. But you saw that now we got a 0 over here as well. So we got the 0 onto this. So now we were left with these 2 things. Are you seeing this is not curable? So this thing is incurable. You cannot cure. You cannot exchange the rows here basically. So there is no equations, so no exchange equations possible which can avoid the 0 pivot. Okay, so this basically is the case where this is incurable. Gaussian elimination cannot cure this. Okay, so in this case we have the infinity many solutions. Okay, is it clear why this elimination basically is uncurable and why it is curable? If you can make an exchange of rows, that's curable that time. If We cannot make the exchange of rows. That time it's incurable. Is it clear?
Yes, sir.
Nice. So this was the first method how we can compute these x, y, and z's. Now you must have that picture in your mind. The picture, for example, every equation that we have, it either, if it is in 2D, it represents a line. If it is in 3D, it represents a plane. If it is in 4D, it represents the hyperplane and things like that. And when we are having these planes, so they some sort of intersect each other at a point, and we want to find that point. So that's our whole point, and that's where this Gaussian elimination comes into the picture. That's a fundamental problem that we are solving. So we want to see what is the cost of elimination. Cost of elimination. Many of you are doing DSA right now, so there you might have seen complexity of algorithms. So complexity, you might have seen that. What is complexity of this algorithm? Let's suppose if you are doing linear search, so you are searching element by element. Okay, so that time you are saying that the complexity of linear search is order of n. Order of n basically means, so it can be order n, it can be constant order, it can be order n square, or order n cube, it can be n factorial even, it can be exponential as well, n to the power something. Let's suppose 2 to the power n or something like this. So what is the meaning of complexity? Let me first explain you the concept of complexity, and then we'll see what is the complexity of doing this Gaussian elimination. So let's suppose I am doing a search on the program. So I have an array of numbers. This is 1, 2, 3, 4, 5, 6. So if I have to find number in it, so I can perform a linear search, let's suppose. So in linear search, what will happen is I'll go element by element and check if that element is equal to the element which I am finding. So if there are n elements, so I'll need n operations. Okay, so I'll need n operations. Let's suppose if I increase the elements, if I make them double, I'll make elements 2n. So how will the complexity increase? So the complexity basically will increase by again 2n, by the factor of 2n again. So this basically means however you want, you are increasing the input, similarly the output is proportional to that. So input basically is directly proportional to the complexity size. So we can say that in complexity this is linear algorithm. Why is it linear algorithm? Because if we are giving 2n, so it's also giving the 2n complexity. If you are increasing it by 3n, so we're having 3n. But some algorithms give us the complexity of order n square. So what I mean by n square is, let's suppose, let's again take the example linear search first. So in the linear search, if we had, for example, 10 elements, so let's suppose you were taking 10 seconds. If you add 20 elements, double than this, the time also became double. So you are getting 40 seconds now. So if you have not 40 seconds, sorry, 20 seconds. So if you have, let's suppose these are number of elements. So if we're adding 30 elements, so the time is getting 30 seconds. So you can see that the time is increasing linearly. So there is no quadratic or cubic growth. So but what if things happen like this? Let's suppose on the input 10, my algorithm or whatsoever I'm taking, that takes, let's suppose, 10 seconds of time. But if I'm making it 20, okay, if I'm making it 20, so what will happen is if the order grew in the n square order, okay, maybe let's suppose from the in the 10 seconds, let's suppose it takes now 200 seconds, let's suppose, or 400 seconds if you directly take the square of this. And now if you add more, if you keep on adding more elements, let's suppose it's excuse me, so this is 100 seconds, let's suppose. If we increase the elements to 20, it now took 400 seconds. If we increase the elements to 30, it now takes 900 seconds. So you can see that whenever we are increasing the input, the output complexity is basically increasing in the quadratic form. So you are sort of squaring these numbers. So that's called, the complexity is quadratic complexity. And if I had to teach a course on algorithms, we'll see what this big O notation means. So there is a theta notation, there is an omega notation. This is called as worst case complexity, average case complexity, and the best case complexity. So I don't want to get in those details, but here just get the thing that we want to see what is the complexity, what is the cost of this elimination. So how many operations does this elimination take? If you see in here, how many operations does this elimination take? Let's suppose we have an matrix that's of size, let's suppose n cross n. That means it has n elements over here till n elements. The first operation, what it does is we make zeros everywhere. Okay, that's the first. What are the operations that we do? We'll do multiplication or division on a row, so that, and then we'll make addition or subtraction, let's call this one operation. Let's suppose we'll call this one operation. So how many operations are there now? So in the first case, how many operations are there? If you see this, so you're making, first is this entry as 0, and then you are, for example, for this first row, all the things get multiplied, and all the thing get multiplied, divided, and then get subtracted, all the elements, if you see it. So there are n elements. Okay, if you see it this way. So how many operations are basically needed is, so the first thing that you will see is you will need n into n minus 1 operations for the first case, if you see that. So you have to compute this. So for this, when you are performing the making all of these entries 0, okay, when you are making all of these entries 0, so your goal is the making these entries 0, but you are basically taking all of this and computing onto this. So this basically is of size n cross n minus 1, and these I'm taking this multiplication or division, addition or subtraction as just one operation. So because here you might be multiplying whole of one whole of a row, and you will be adding or subtracting to the whole of the row. So here if you see the submatrix, this part of the matrix, so you can see it is the size n minus n by n minus 1. So the first takes n square minus n operations, and accordingly you will do the operations. So how many operations do you take? It basically is basically n square, then it will be n minus 1 square plus n minus 2 square, and so on. Again, to make it clear, so these were our n rows. So our first task was to make all of these as zeros. Okay, so in that pursuit, what we did is we applied operations onto these things, onto this many rows. So how many operations? So if I just compute this multiplication and addition as just one operation, basically there are two operations, but I'll just say they are one operation. So if they are one operation, so here the elements remained basically are n into n minus 1. Okay, so the total elements are n into n are total elements. So but I'm not doing anything with the first row, that's why I'm subtracting this one from here. So in the first iteration, in the first step, I'm making these many steps. So in the second step, so because now the pivot is this, I'll make these entries as 0. So in the initial state, let's suppose I'll make n square, roughly n square operations, and then in the second iteration I'll make n minus 1 square operations, and the third I'll make n minus 2 whole square, n minus 3 till 1 square operations. And you know that these terms are again there, so we can just subtract this. We can subtract this. Initially we subtracted n minus 1, n minus 2, and that will be 1 plus 2 plus till n. Okay, if you sort of compute this, this comes to n cube minus n divided by 3. So this is the complexity it takes. So this basically algorithm is cubic algorithm. Okay, so it takes 1 over 3. If you tell me exact, n cube minus n, these many operations does it take. When I'm saying that addition or and subtraction plus division or multiplication, this as one operation. So these many number of operations this takes, and this is called as the complexity. This sort of gives us an estimate. So if you have, for example, let's suppose 9 elements, so if it takes, let's suppose, let's take this 10. We had in a matrix, we had let's suppose 10 cross 10, 100 elements. Let's suppose this takes some 10 seconds, let's suppose. So if you now increase the element, so if you make this element as 10,000, so what will happen to the complexity? It will sort of in order of n cube, so it will cube the time. So it is not just linear, it is not the complexity is not linear, it will sort of cube this. If the computation was taken 1 second earlier, so if you just double the input, the output, the time taken will not be doubled, it will be basically just time raised power that cube. Is the complexity of this clear? So this is the cost of elimination. So basically, if you ask me what is the cost of elimination, you can just give order of n cube. This is the time this elimination takes. But there are other algorithms by which you can decrease this time. But here I wanted to introduce you with the complexity. So that's a really important thing, and also want to sort of introduce you to the counting as well. So you saw how we counted these things. So because in the next chapters or next sessions, because when we have to deal with probability and things, there we will see permutations, combination, and these counting problems do occur there. So here, just make sure do you understand this. How do we count these steps? Is it clear? I make a just rough estimate of order n cube, and I did not do the exact calculation, but I just gave you the idea how to do the exact calculation. You can just take the pen and paper at your ease, then do the calculations. How do we got this order of n cube, or maybe this exact value 1 by 3 n cube minus n? So is it clear?
Yes, sir.
Okay, this is the cost of elimination. The thing I wanted you to see is that elimination is not actually a bad process. So this is just order n cube. So if you take determinants and solve this equation, it becomes really scary. So there, if you solve the equation by using the determinants, so I'll say every software, every Python package or every MATLAB package, it uses this Gaussian elimination. So underneath the hood, if you give it equations and if you tell it to solve these equations, even if you had the scientific calculator and you make these equations, so it basically uses this Gaussian elimination. That's the power of Gaussian elimination. Is it clear? If it's clear, then we'll move on to the
Yes, sir.
next part. As we have done this matrix multiplication, we have done everything regarding that, and now it becomes easy for me to explain you what I call that elementary operation. So I'll again go to the elementary operations. Just put your focus here, because here I need your utmost focus. So again, if I write these equations, so how I can write the elimination step? Let's suppose I have that if I wrote that R1 is basically R1 minus twice R2, something like this. So this can be captured into a matrix. So basically this was a move. So if we had a matrix like 1 2 3 4, okay, if I had to make this entry as 0, let's suppose I have to make this entry as 0. So what did I do in Gaussian elimination? It was basically I just took R2 and I said R2 minus 3 times of R1, because this was 3. I'll make this 3, this entry as 3, then I'll subtract them. So this is what I want. So how to achieve this basically is I can make a matrix out of this, which I just will multiply with this. So how to do that? So if I do 1 2 3 and 4, so now you know, because now the first column is left as it is, so we'll do nothing with the first row, sorry. The first row is left as it is because we're dealing with the second row. So if you again know the ways of matrix multiplication, yesterday I showed you the column way of matrix multiplication. You take this column, multiply it with this, you take this column, multiply it with this. So if I want to keep the first row unchanged, so what I'll do is I'll put 1 over here, because this will get multiplied to this thing. Okay, so again if I put 1 here, so what will be the output? So it will be 1 2, because I am leaving this row unchanged, but I have to change this row. I have to change this R2 minus R3. So how I can represent this in matrix form? So basically R2, it should get subtracted with 3 times R1. So first I'll multiply 3 with R1, so I'll put 3 here, so this R1 will get multiplied by 3 times. Then I'll subtract this 3, so it should be minus 3. I'll subtract it from that, and then I'll write R2 as it is. So this matrix basically is the representation of this. So we call this an elementary matrix. Is this clear how we got this elementary matrix? Is it clear? Is it clear?
Yes, sir.
Okay, so I just wanted to prove the same thing. So here the matrix was 1 2 3 4. So this was 1 2 3 4. The operation that we performed was R2 basically should give R2 minus 3 times R1. So what should it give is, so if you see, if you perform this operation, so the first row will remain as it is, and the second row, what will happen to the second row is 3 minus 3 is 0. So again 3 2s are 6, 4 minus 6 is basically minus 2. So this should happen. So again I created this matrix, this elementary matrix out of that. So how to get this elementary matrix? 1 2 3 and 4. So I said the first row I have to do nothing, so I put 1 0. For the second row I have to multiply it with minus 3, this, and then add it to the second row. So let's now perform this computation in the matrix form and see whether we'll get this same result. Okay, now you know that how to perform this. Row by this 1 1s are 1, 1 0, so this will be 1. Okay, so 1 2 is 2 and 0, so this will be 2. And now we have here minus 3 multiplied by 1 is minus 3, and then 3, this is 0, and then 3, that is minus 6, and 1, this is minus 2 now. So did you saw that this elementary matrix multiplied with the original matrix, we got the similar thing. So we can represent these moves by the elementary matrices. Is it clear? So any
Yes,
elementary
sir.
operation basically can be represented by using the elementary matrices. So we call these elementary matrices, we represent these elementary matrices by using the symbol E. and we will not sometimes write this directly, and we can just write an elementary matrix out of that. Is it clear? Any matrix, you know the what's the meaning of identity matrix and stuff like that. So any matrix that does nothing is basically identity matrix. So what matrix basically is, it is just giving us that linear transformation. You should have that thing in the mind. Okay, so if I want to exchange rows, let's suppose this is 2, 3, 4, 5. This is the question for you guys, so I want you to answer. So let's suppose if I want 4, 5 should be here and 2, 3 should be here. So this, there should be some transformation. So I know this transformation basically is change row 1 with row 2. So how can I represent that in elementary matrix representation? So how can I do that? So what should I put in here so that this should be the result? Rian, can you give me the answer? Rian, are you there?
Sir, I think you just have to exchange like row 1 and row 2.
So I have to exchange row 1 and row 2. So what should be the values of this matrix? Because this is our elementary matrix now. So what I
Hmm.
want is, I want you to fill in these values so that I get this matrix out of this. I want to represent this elementary operation by using the matrix.
Hmm. Don't know, sir.
So what should be the values? If you understood this part, so it should be easy. This part should be easy.
Hmm.
Okay, let's have this question as it is. I'll again maybe explain to you this operation. Let's suppose we have a matrix 1 2 6 1. Okay, and we want to get, let's suppose, 0 over here. Okay, so in order to get 0, what I can do is r2 is basically equal to r2 minus 6 times r1. So how I can represent this with matrix? The first row is unchanged, so I'll just do 1 comma 0, because this 1 will get multiplied with whole of this row, and this 0 will get multiplied with the whole of this row to create the row of the first, because I want 1 to be intact. That's the reason I put 1 and 0 over here. For the second row, I know that I have to put the first row should get multiplied with 6. Okay, I'll put 6. Then it should be subtracted as well, so I'll put minus 6 over here. I'll subtract it from the second row, so this row should get multiplied with 1. So this is the representation of this elementary operation. So this is our elementary matrix, this is the operation. So now I'm telling you that, tell me how to exchange these rows. So I have 2 3 and 4 5. So I want to exchange 4 5 and 2 3. So I want to exchange the row 1 and row 2. I want to just represent this. So the first entry here should be 4 5. So you know that this coefficient, if I said a, b and c, d, this a will get multiplied to 2 3, this b will get multiplied to 4 5 to produce this row. Salim, can you give me the answer to this? So what should be the entry? What should I put in this matrix so as to get this matrix? But Rian, was it clear? Was the elementary transformations clear? How we do these elementary transformation? How we represent them in matrix?
Yes, sir.
Okay, let me do it for you. Then I'll expect you guys to do the next problem. So I have to get 4 5 over here. So I know. So this will be basically the linear combination of these two things. So what I'll do is, because I want 0 of this row, so I'll put 0 of this row, and I want 1 of this row, I'll put 1 over here. Okay, and now I need to exchange it. I'll again say I need 1 of this row now and 0 of this row. So this here tells me to exchange the first and second row. So if you see it here, so this will exchange the first and second rows and give me the answer there. Just do the matrix multiplication now the normal way you used to do. 0 multiplied by 2 is 0, 1 multiplied by 4 is 4, so this is 4 here. So then 0 3 is 0, then 1 5 is 5, so 5 is here. So this checks out. Okay, let me again make a matrix. Let's suppose 1 2 4 2 0 1 1 8 minus 2. Now I want to exchange row 1 with row 4, row 3, sorry. So can you now tell me what to do with this row? What is the elementary matrix right here that I can write so that I get the answer as 1 8 minus 2 1 2 4 2 0 and 1. So this should be my answer. This is what I need.
Sir, first row should be 0 0 1.
So
second
first row
zero
should
one
be
zero,
0 0 1. Nice.
second 0 1 0,
0 1 0. Okay.
and the third one should be third one should be yes 1 0 0.
1 0 0. Nice. So this is the elementary matrix. Is it clear, Omar? Are you there? Is it clear? Okay. So you now understood the concept of these elementary matrices. So how to capture these elementary operations into this elementary matrix. So that's the concept. So now if we have a matrix, let's suppose A. Okay, if you have this matrix A, and you are performing certain elementary operations, and we can call them E1, and we can call them E1, E2, E3, and so on. For example, there's a bigger matrix, so it can be till En. Okay, so as to get this lower triangular matrix, and we can put something in there. So this is what we'll do. So we can just club this matrix together and represent it as just one matrix, capital big capital E. Okay, so that will be in a matrix if you multiply that. And in our case, for example, we had Ax is equal to V. That was our equation. Ax is equal to V. Now we want to find this x. So what we did is we performed certain operations on this, and parallelly we performed the same operations onto this. So what we did is this A multiplied by this A was multiplied by first one elementary matrix, then second, then the second, then third, and so on till n. Okay, and similar thing was done to this matrix. Similar thing was done to this V. So this V was multiplied with again E1, E2 until En. This, let's suppose, got changed to EAX, and this will be equal to EV. Okay, so now this EA matrix was our coefficient matrix. Whatever it got changed to something. Let's call that matrix as, let's suppose, W X, and that was equal to this EV got equal to V dash. Let's suppose. So now we convert these two matrices, and we can now do the back substitution. If you just see the triangular matrix, just have this notion in mind. So everything in here is basically a matrix. So if you perform any operation, that is basic, that can be represented using a matrix. Okay. So if I give you, let's suppose, just to close this topic over here, so I can give you what's called as permutation matrix. Permutation matrix. What is that? So if I have, let's suppose, 3 cross 3 case. Okay, so how many permutations is possible? I can exchange 1 and 2 row, I can exchange 2 and 3, I can exchange 1 and 3, like this. So I can have, because there are 3 rows, so I can have 3 factorial ways of changing them. I can have 3 factorial permutations, that is 6 ways. Let's suppose the first way is I'll do nothing. This is no change. If I want to change the first row and the third row, first row and the second row, so how to change that? First row with the second row. So first row should be changed with the second row, so I'll put 0 1 0. Okay, I need, for example, if there is a matrix A B C D E F G H I, so if I want to change sort of these two rows, oh sorry, these two rows, first and second. So what I want to do is, so here this should be the entry, because I want 0 of this and 1 of this, and now again I want 1 of this here, 0 and 0. Here this is R1 exchanged with R2, and this will be 0 0 1. In the similar fashion, I can make 6 combinations, 6 such matrices. So if I want to enumerate all of these, can you enumerate all of these? So second thing will be change R1 with R3. So let's suppose 0 R1 with R3. So R3 should be here. So nothing should happen to R2. So R3 should get changed to R1. Okay. So what are the other permutations? Let's suppose I want to change R2 and R3. So first row should remain as it is. The second row basically should get changed with the third row. And the third row should basically get changed with the second row. So such a way there will be 6 permutations like this. If you enumerate, this is the first one, second, third, and you can make the other 3 as well. Okay, that is the concept of these permutation matrices. Sometimes you want to do the elementary transformations with the permutations as well. So it can be do some elementary transformation and with the row exchange, and you can put the P also in there. So PEA, if you see it written anywhere, this basically means you applied some elementary transformation that was a matrix without the row exchanges. So if you put this P, that basically means you did some row exchange. Is it clear? Nice. Now you know the what's the difference between this triangular matrix, and now we'll go to the inverses back. So we'll again touch the topic of inverses. So you now know that what is the meaning of inverse. So let's suppose we had a vector x and y, a generic vector x, and we applied some transformation a b c d onto this, and it took a vector, for example, let's suppose to x dash and y dash. It took a vector x dash and to y dash. If we again apply the inverse of the transformation of this, let's suppose this is our matrix A. If we applied A inverse onto this, A inverse onto this, so this should get back into x and y. That's the meaning of inverse. So basically inverse means if I have a transformation A, and if I applied it onto x, and it gave some, for example, let's suppose vector v. If I now apply A inverse onto this, okay, so this should give me back x. So A inverse should be equal to x if I apply x onto this. So now from this I conclude yesterday that A inverse A basically is identity. So if you have a transformation A and you undo this transformation I inverse, so you A inverse, so you will get this identity matrix. Now we want to find this inverse. Okay, that's a concept, and we want to find this inverse. Yesterday we introduced this concept. Now we will need to find the first thing that we saw is Gaussian elimination. Why did I introduce the Gaussian elimination? Because it will be helpful in here. And you know that we saw that determinant should not be equal to 0, otherwise it becomes that it becomes the singular case which we cannot cure because it squishes the whole space if it is 3D to the 2D or 1D. Let's now find the inverse. Let's suppose I have a matrix. Let's take again the matrix 1 2 uh, 3 and 4. Let's suppose this is the matrix. Okay, so this is the matrix. So if I apply any x y onto this, so this will do something to this vector. It will take this vector to somewhere, but I want to compute the inverse of this. But I know I want to find how to find that inverse. How to I know that ax, this is a for let's suppose, and this is vector x. And if I apply the inverse onto this, this should again become x. That is the whole point. So a inverse a should be equal to I. So how to compute this basically is, so I'll have this matrix A. Okay, I want to get this matrix I. Okay, I'll perform these certain elementary transformations over, and the same elementary transformation will be performed here. Okay, so I'll perform this transformations over here and perform the similar transformations onto this I matrix as well. So I'll make this A should this A, whatever I get here, let's suppose I get a matrix of E over here. So this E, and here I'll again get EI. So if this became if this thing became the identity now, so I can surely say that this E is basically equal to A inverse. Again, I'll make it clear. So the thing here is I had a matrix, let's suppose A. That matrix was equal to A, B, C, and D, let's suppose. This was the matrix. So I can write it like this: A, X was equal to something. But what I want is, I want AX, it should be equal to identity. And how I can achieve the identity, I have to sort of operate onto this A. So because I told you that every elementary operation can be seen as a matrix, so I'll just multiply it with some elementary matrix E. So I'll also make this E. So how I'll make it, I'll perform elementary operation in such a way so that I'll make whole of the product as identity. Okay, so if this is I, that means I x is equal to EI now. Okay, so now Ix, you know that is equal to x is equal to E of what happens, like this EI will get changed. So this will become basically the inverse. So I'll be sure that I applied inverse onto this. So this will become the inverse. So whatever will happen to the whole matrix will become the inverse. So let me again tell you, and we'll take a example. It will be clear with the example. So let's take an example. I have an example written here. Let me check that because it gets easy for me to just cross check the values. Let's suppose will take a bigger matrix: 2, 1, 1, 4, -6, and 0, -2, 7, and 2. Okay, so this is our equation. So these are three values. Okay, this is and then we have x1, x2, and x3 over here. And let's suppose it's equal to something, and let's take it to even into. And I want to get inverse of this matrix. So how to get inverse of this matrix basically is, you just have to do one thing. You have to make this as identity by using the elementary transformation, by using the elementary operations. By using the elementary operations, you have to make all of this You have to make this thing as identity, and then you have to again do the same thing with the identity over here. So what you will do is you will use what is called as Gauss-Jordan method. You know the Gauss, it was elimination, Gauss elimination, and Gauss-Jordan method basically says just augment this identity onto this. So it will be like this. So we had 2 1 1 4 6 this. So I'll just select this matrix. So this was our matrix for which we want to find the inverse. I'll copy whole of this. So this is our matrix. So again, what Jordan said that you just augment this with the identity. So identity is 1 0 0 0 1 0 0 0 1. So now, as I told you that in here, whatever you apply onto this A, you have to do the similar thing to this I. So if we get this A became identity, so this I will basically become the inverse. So that we proved the mathematics. Now we want to see what will happen. So in the identity, the first case is I want to make this as 1 and I want to make these entries as 0. Okay. So anything is possible here. So the operations that we can exchange rows, we can exchange the rows, and we can multiply or divide a row, we can add or subtract any row from any other row. So that these are the three operations. So if I can divide this by 2, so I'll get 1 over here. So I'll get 1.5, 0.5. I just divided these things. The similar thing I have to do it here. So I'll get 0.5 over here, 0.5, 0 and 0. That's the first thing I did it. In the second row, I did nothing. I'm just giving you the operation so that how to do it. Okay. So now I need zeros over here. Okay. So how to get the zeros? I can multiply, I can divide this 6 with the 12 to get this 0.5. Okay, and I'll subtract these things from here, and then you will get the zeros. And what I mean by this, we can do this cumbersome process, but the whole point is that this matrix will get changed to something and this will get changed to something. So this matrix basically will get changed to, because 1 0 0, that's our goal, 0 1 0 and 0 0 1. So this matrix will get transformed to this, and according to this matrix will also get changed. This matrix will get changed to, let's suppose, something A B C D E F G H I. So this is the inverse. So this will be the A inverse. So if we had A was R this. So this will be the A inverse of it. This is the method of finding the A inverse. Is the method clear? What is Gauss-Jordan method? Is it clear?
Yes, sir.
The Gauss-Jordan method basically says make this as the make that as identity. Make the A matrix that we had as identity, and whatever happens to the identity will become the inverse of that matrix. Okay. So this is the Gauss-Jordan method, and we'll give a lot of examples in the assignment so that it becomes easy for you as well. So when will this inverse not exist? So existence of inverse is the question. Existence of inverse. When will it not happen? So there will be no inverse. That's a really interesting question. So if you have a matrix, so when will the inverse not be there? And we'll see that. I told you the determinant should not equal to 0. Otherwise the inverse will not be there. So why should it not be there? So for example, we know that Ax is equal to 0. Let's suppose this A is equal to 0 basically means if we have a matrix, let's suppose 1 2 and let's suppose 3 6, if this is a matrix. Okay, and I'll put some x1 and x2. Okay, I'm putting some values over here. Let's suppose -3 and 4. Let's say. So here you can see in this matrix over here, you can clearly see that the rows are dependent. This sorry, the column is dependent. This column basically can be obtained from this column. So now if you see that if you see the representation that we showed you geometrically, so what will happen basically is, so these two vectors span a single line. So they all only span a single line because they lie 1 2 base. Suppose 1 2 lies on this. For example, this is 1 2, and 3 6 basically is 3 times of this. So you have 3 times of this line. So they lie on the single line. So initially, if you had some matrix, let's suppose A, and when it was applied to some x, so if it squished the space in the 2D case, if it made that a line in 1D, or if it just squished to the 0 dimension. So here we can say that the inverse won't exist because you cannot invert this. Now out of a line you cannot create the whole 2D plane. So you had the 2D plane in the initially you had 2D plane, you had some vectors, let's suppose this vector and this vector, and they were sort of spanning the whole plane. Now you applied some transformation. What happened is, let's suppose it took these vectors onto a similar line like this, onto a single line. Now from this single line you cannot undo this transformation. Or let's suppose it took it took the vectors to 0, all the vectors to it took to 0, it switched the space onto the 0. Now from the 0 you cannot get all the other vectors. So if we had a transformation like this to this, and transformation happened and it made the transformation like this, still these two vectors after transformation, they were still in the same 2D plane and they were able to span the whole plane. So you can get any vector out of this. So basically in inverse what we do is, if we had an original vector like this and we apply a transformation and that vector went onto this, so in the transformation we did it from here to here, in the inverse we'll get this vector back onto this. So that's the whole point. So a x basically is x if we apply the inverse onto here, and this basically will give the identity. So that's the whole point of inverse. Now I'm saying that when inverse won't exist. So inverse won't exist if, let's suppose we have a transformation like this. Let's suppose this is a transformation and it took these vectors, we have transformation t, it took these vectors suppose onto a single line or maybe onto a point. So now you cannot get all the vectors onto this, you can only get the axis of vectors on this line, and for this point you can get no vectors. So if you say, let's suppose, and this matrix has an inverse, let's say this 1, 2, 3 and 6, this is the matrix. I told you that this is non-invertible. Why? Because it squishes the whole space onto a line. All these, both of these vectors basically takes this. If you say, let's suppose this has an inverse, so that means we have an x1 and x2 over here. So that was, let's suppose, equal to some value 2, 3. That basically we can say ax is equal to 0. Okay, we can find some non-zero values of x for which this equation ax will become equal to 0. Now you cannot basically undo it. Now you know that if you have some value, let's suppose this x1 and x2 will have some definite values. This x1 and x2 will have some definite values. So for that what I want is, if they have definite values and this x1 and x2, they are both not equal to 0. But you can say, if you just apply the inverse, a inverse of x is equal to 0. Now this shows that x is equal to 0. Basically that is the contradiction with the assumption. So I am proving something with the contradiction. So that's again a concept, proof by contradiction. Prove a contradiction. What I'm saying is, let's suppose this matrix has an inverse. So I'm saying 1, 2, 3, 6. Okay, so I'm giving x1 and x2 over here. Let's say the value should be 4 and 8. So I know that if I put x1 is equal to 1 and x2 is equal to 1, so I'll get this value, I'll get this 4, because I'm taking one of this and one of this to give me this 4, 8. Okay, I'm taking one of this to give me this 4, 8. So I have the non-zero values. But what is the meaning of inverse? The meaning of inverse is basically, if I have this ax, okay, so if I have some values of x for which I can take this to 0, okay, for the non-zero values, let's suppose for the non-zero values, if I can take this by using this a, I can take this x to 0 for this non-zero values x. Let's suppose we have this 0, 0 over here. I have this, let's suppose I'll make this 0, 0 now. So if you understood this part, I can erase this, I can make this 0, 0. So I'm saying, let's put some values onto this x1 and x2 now, so that it becomes 0, this x1. So I can write this x1 is equal to 3, x1 is equal to 3, and x2 is equal to -1. So both of these are not equal to 0. So now this is equation A and this is our x. Okay, you can see this ax is equal to 0 is satisfied in this equation, and you know that x is not equal to 0 for sure. But if you say that the inverse exists for this matrix, so that you're claiming that a inverse should be equal to x is equal to a inverse of 0. I'm multiplying inverse on both the sides. Now you know this becomes identity. This is identity of x. This is equal to 0. So you are saying that x is equal to 0, but x basically was equal to non-zero. This is what we showed. So this is a contradiction. So if we have a case like this where these rows are linearly dependent, you can say that inverse does not exist. Or if you compute the determinant as well, 6 ones are 6 minus 2 is 6. So determinant is also equal to 0 here. So this is a non-singular case. So mathematically I showed you the proof why the inverse will not occur basically for the matrices in which the rows are, in which these columns are linearly dependent. Is it clear? Is it clear?
Yes, sir.
Nice. So that was the case of this non-singularity and inverses. And then we have the last concept for today is transpose of matrices. Okay, so I'll take this transpose of matrices. So what is the transpose of matrix? So if we have a matrix A, which is AB, CD, and EF, A transpose is changing the rows into columns and columns into rows. So that is, I'll write A, E, C, E, and B, D, F. So this is what I call as transpose. So mathematically, how can I write it? So I can say if I have A transpose, excuse me, and if I want its ij entry, so that will be equal to take A matrix and take its ji entry. This represents row and this represents column. Again, here I am changing, this represents column and this represents row. That is the concept of this transpose. Okay, so mathematically I showed you. So let's suppose now I'll take a matrix 1, 2, 4, 5. This is A, and if I want A transpose, that will be equal to 1, 4, 2, 5. Okay, so this is the concept of transposes. So where is it basically used? So there are properties of transpose. Let's suppose we have a matrix A and we have a matrix B. Let's multiply them together. The first property of transpose is that if we transpose whole of this together and we multiply these matrices together, then we put a transpose. So this is equal to B transpose A transpose. Take it as an exercise to prove it. Mathematically, you can prove it, or maybe you can prove it by visual representations. But they should be an easy exercise for you people. And the other thing is, now you know how to compute the inverses. So if you have an A inverse, okay. So if you transpose this, so again a property is that you can just first transpose then compute the inverse. So this is again left as an exercise for you how to prove this. So these are the properties of inverses. So if you have AB transpose, this is equal to BT and AT transpose. So if you have an inverse, A inverse transpose, and you can take that transpose of matrix first and then you can invert the matrix. Okay, then there is a concept of symmetric matrices. Symmetric matrices or symmetric matrix. So let's suppose we have a matrix like this. We'll take a matrix bigger. So we have 1, 2, 3, 4, 5. Let's suppose we'll take 2 over here. So now this is A. If I take transpose of this matrix, so I'll make this row over here 1, 2, 3. So I'll make this column again a row 2, 4, 5. Make this 3, 5, 2. So I transpose this matrix. So this is the A transpose. If you see that A is equal to A transpose, so we call these matrices as symmetric matrices. So any matrix in which the A is equal to its transpose are called symmetric matrices or symmetric matrix. So I give an example over here. So so how can I write mathematically? If Aij is equal to Aji in matrix, we call that matrix as symmetric matrix. Why am I introducing all these concepts? Because they will be used in our subsequent chapters when we'll be reading about decompositions and stuff like that. Okay. So here I'll sort of terminate or maybe end this session. And here we have completed basics of algebra, basics of linear algebra. So this is the basics of algebra are over. Now we'll go into the more mathematical details of the algebra. So in the next subsequent sections, what we will read, the first thing we'll read about what is the meaning of a vector space. What is the meaning of vector space? Okay. Then we'll see the concepts, for example, like what are eigenvalues, what is that decomposition and stuff like that. Maybe I'll stop the recording over here.